talk about, having talked about convergence of sequences of functions, we now talk about convergence of series of functions. So the point to note here is that all the discussion that we have had on sequences of functions already applies naturally to series of functions. And so all our discussions extend to series of functions. Right? Series of functions would look like, say, summation 0 to infinity gn of x, right? Because after all, this is in fact just the limit of the sequence of finite sums, right? From 0 to n gn of x. So since we know how to talk about the limit of sequences of this form, we therefore already know how to deal with series of functions, right? We have already looked in fact at power series, right? So therefore it is meaningful to talk about uniformly convergent and uniformly Cauchy series of functions using very analogous in terms of the sequence of running sums, right? It is thus meaningful uniformly convergent or Cauchy series of functions. Right, so specifically a series would be uniformly convergent if the sequence of running sums is uniformly convergent. A series is uniformly Cauchy if the corresponding sequence of running sums is uniformly Cauchy. Right, so straightforward application. As an illustration of this, let me state a simple fact. I'll write it as a lemma, but it's in fact trivially following from what we have already said. So consider the series of functions on S, which is a subset of R, if each Gn is continuous and the series converges uniformly. Then the series represents a continuous function on S, right? And why does this follow? This follows from the fact that uniform limits of continuous functions are continuous, right? Because we know that the series is converging uniformly, and additionally that because each of the GNs are continuous, every element of this running sum is in fact a continuous function, right? So therefore, by applying the previous result, it follows that the limit of this series will in fact, which is exactly what we are representing in this manner, it in fact represents a continuous function on S. All right. So therefore, I don't need to separately define what it means for a series of functions to be uniformly convergent and uniformly Cauchy. So we can move straight to proving results on series of functions. So the first of these is going to be the Weierstrass M test. So this is a very useful test to argue that a series of functions is in fact uniformly convergent. Okay, so let mk be a sequence of non-negative reals such that the series summation mk converges. Now, if absolute value of gk of x is going to be upper bounded by mk for all x in S, right, which is some subset of R, then the series gk of x converges uniformly on S, right? So this gives you a sufficient condition for uniform convergence of a series of functions, namely that if each of the entries being summed, right, can be upper bounded by some constant mk, and if the summation of mk is in fact convergent, so the series summation mk is convergent, then in fact the series of functions summation gk of x in fact converges uniformly on S. Okay, so the proof is in fact going to be remarkably straightforward. So the first thing we note is that since this series converges, the corresponding sequence of running sums should satisfy the Cauchy criteria, right? It satisfies okay, that is, if you fix any epsilon greater than 0, then there exists a capital N such that summation from m to n of mk must be less than epsilon for all n greater than equal to m greater than capital N. Right, so this follows from the fact that the sequence of running sums of mk corresponds to a convergent sequence and therefore a Cauchy sequence, right? Thus, if n greater than equal to m is greater than n, if you now look at the summation k equals m through n gk of x, yeah, this in turn is less than or equal to summation again from m to n of absolute value of gk of x. This is your triangle inequality, which in turn is less than or equal to the summation from n to n of mk by the hypothesis, which in turn is less than epsilon. Right? So what we have essentially proved is that if you look at the series of functions summation gk of x, this guy is uniformly Cauchy. Right? And since uniformly Cauchy sequences of functions are in fact also uniformly convergent, the result follows. It is uniformly convergent. Right, so we will use the Weierstrass M series M test quite extensively, particularly when we are talking about convergence of power series going forward, and we will do an example very shortly. But the basic idea is that if you are able to upper bound gk of x by a certain positive or non-negative constant mk such that the mk's are summable, then you can in fact argue that this series is uniformly convergent. Okay, and in this case you are able to show uniform convergence of the series without in fact identifying the limit itself, right? Because what you're really showing is uniformly Cauchy. All right. So one more result along these lines. If the series summation Gn of x converges uniformly, then uniformly, yeah, on S, right, that's implicit, then limit n tends to infinity, we'll just put that in on S, then limit n tends to infinity of the supremum of the values taken by Gn of x over x in S, this limit must be 0. Okay, so this is analogous to saying that if you have a Cauchy sequence, then the entries of the sequence must in fact converge to 0, right? We know this. This is in fact that provides a necessary condition for convergence or Cauchiness of a sequence of reals. This is the analogous version of that too, applied to series of functions. So if the series converges uniformly, then in fact if you look at the summand functions, the supremum of the values taken by them over S should in fact converge to 0, then tends to infinity. All right, the proof as expected should be straightforward. A uniformly convergent series is also uniformly Cauchy. Right, so if I fix epsilon greater than 0, there exists a capital N such that summation Gn of x from m to n, oh, I shouldn't use n in that case, let me use k, summation k running from m to n, Gn of x is in fact less than epsilon for all x in S and n greater than equal to m greater than capital N. Okay, which in turn implies, so if I just take m to be equal to n, that would imply that Gn of x in absolute value must be less than epsilon for all x in S and for all n greater than capital N, right? Which in turn implies that if you now take the supremum of the absolute values of Gn of x over x in S, this is in fact going to be less than or equal to epsilon, right, for all n greater than n. Right, and that is all we need to prove, that in fact this sequence here converges to 0 as n tends to infinity. Okay, so this is now a consequence of what we have proved is a consequence of uniform convergence or uniform Cauchiness of a series of functions, right? That if you look at the entries of the series, those entries of the series, the supremum of the absolute values taken over the set under consideration must in fact converge to 0 as n tends to infinity. All right, so now what we are going to do is come up or rather demonstrate an example which applies both the Weierstrass M test as well as this lemma that we have just stated. Okay, here is the example. This example involves a power series, and we will have a lot more to talk about power series going forward. Okay, now consider, well, it doesn't quite matter whether it's from 1 or 0, so let me just say 1 to infinity, or let's say 0 to infinity. 0 to infinity, 2 raised to minus n, x raised to n. This is my power series. My claim is that this represents a continuous function on the interval from -2 to 2, but the convergence is not uniform. Okay, so what I've written here is really the claim that we will prove as we analyze this example. Okay, so firstly, by staring at this series, you should be able to quickly check that the radius of convergence in this case is equal to 2. Okay, you can go back and recall the definition of the radius of convergence of a power series. So the radius of convergence in this case is 2. In other words, for absolute value of x less than 2, we know that there is pointwise convergence of this power series. Okay, now the way we are going to show that this represents a continuous function on the interval from -2 to 2 is in fact as follows. So pick a that lies between 0 and 2 strictly. Okay, now in this case we basically will first look at this in the closed interval from -a to a. So for x lying in the interval from -a to a, the thing to note is that if you look at 2 raised to minus n times xn, this thing in absolute value is in fact going to be upper bounded by a by 2 raised to n. Okay, and to apply the Weierstrass M test, think of this as mn. Now, since a is strictly less than 2, note that this fellow summation mn in fact converges, right? That's just a geometric sum. So by the Weierstrass M test, we know that the power series is in fact uniformly convergent in this interval from -a to a. Right? Now, since you have uniform convergence over this interval, it follows that in fact the power series is in fact also continuous in the interval from -a to a, right? Because the uniform limit of a series of functions is, which is continuous, right, is also the continuity of the elements of the series that are being summed is obvious. So therefore, from the continuity of those guys, the continuity of the GNs, so to speak, the continuity of the limit now follows since we have uniform convergence. So the power series is continuous on -a to a. Right? Now, since a can be any number less than 2, since a may take any value in the interval from 0 to 2, the continuity over the open interval from -2 to 2 follows. Okay, you should think about this carefully and convince yourself that this is true. Since continuity on the closed interval from -a to a follows for every a between 0 and 2, in fact, you can argue that the power series is continuous on the open interval from -2 to 2. How? Well, you pick any point in this open interval. I can enclose it within an interval of the form -a to a, right? And so therefore, you know that you have continuity at that point, right? So we therefore know that this power series is represents a continuous function over the interval from -2 to 2, where 2 is in fact the radius of convergence. Okay, now how do you argue that the convergence is not uniform? Well, all you have to do is look at the supremum. So let me represent this as gn of x. The supremum of the absolute value of gn of x for x running from -2 to 2 Now you should think about this as x runs from -2 to 2. If you look at the supremum of this, the supremum of the values taken by gn of x in absolute value is in fact going to be 1, right? Because as x approaches 2 or -2, specifically as x approaches 2, absolute value of gn of x will actually tend to 1. So the supremum over this set is in fact going to be equal to 1, right? So since this supremum sequence does not tend to 0, it follows that the convergence is not uniform. Because had the convergence been uniform, then this sequence should have had a limit of 0 as n tends to infinity. Okay, so interestingly, if you look at the power series, it is uniformly convergent on any closed interval of the form -a to a, so long as a is strictly less than 2. However, the convergence is in fact not uniform over the entire open interval -2 to 2. Okay, so this illustrates both the application of the Weierstrass M-test as well as the necessary condition that we derived in the lemma just before. Okay, so we will stop here and talk next in detail about power series.